Okay, hello everyone. So in this class, we're going to continue our discussion on the particulate matter. So before we introduce the new contents, let's first have a quick recap. So last class, we basically give two examples of air pollutants, right? So those are not conventional air pollutants because at first people thought that they're good for the society or for the benefit of human. But later we realized that these gas pollutants can actually lead to some disasters in our ecosystem. For example, the CFC, the chlorofluorocarbon, it can lead to the ozone depletion. And this is specifically talking about the ozone in the stratosphere. And then also, I think this is more of a recent matter that people found that the greenhouse gas species, especially the carbon dioxide, can lead to the climate change or the global warming. So that's why all the government need to work together, because the emission of these greenhouse gas species is kind of a required thing for the growth of the economy, because everyone have to use or have to rely on fossil fuel to generate energy or just generate power for the for running the vehicles, right? And then we also started a little bit about the particulate matter, and we introduced how the particulate matter might scatter light and lead to basically different colors that we see in our daily lives, right? So as I said, the PM can actually pose an effect on all aspects of our daily life. For example, can scatter light, and that's what gave us the color of the sky, or the color during the basically the color of this during the sunset, right? Which we have the red color, and I'll talk about that later on. So basically, these particles can form clouds, and then they can lead to basically they can get generated by these combustion activities, or lead to rainfall, right? They can also pose an effect on the health. And at the same time, a lot of these nano-engineered devices are actually using these particulate matter to boost up their performance. So just as a, let's say, a reintroduce, basically under different PM concentrations, we're going to have very drastically different visibilities. And this is because of the scattering that's caused by these particles, right? As we said, if there are no particles, it doesn't matter how far an apple is away from the eye, right? We can always see that. But if there are particles, then what the lights that's emitted by the or reflected by the apple are going to get scattered all the way around, right? So the final fraction of light that's reaching the human eye is going to be just a little bit of the original light. So the intensity is reduced, and that's what gives us a hazy view when the particle concentration is very high. Right. So basically, the particles will interfere the propagation of light, which further decreases contrast. So we also introduced that basically the color that we see every day is because of the particles, or because of these suspended or aerosols that's scattering the light. So the reason why the sky looks blue during the daytime is because a large fraction of our visible light, actually, a large fraction of the solar radiation is in the visible range, which has wavelengths of around hundreds of nanometers. But at the same time, the suspended particles in the air are actually just within the shorter wavelength band. For example, just a few hundred nanometers, which means that basically these particles are going to scatter more light, mainly because their diameter is very similar to the wavelengths of these short wavelengths solar radiation. So basically they're going to be mainly scattering the light of this blue range, and basically the blue light is scattered out, and that's why we can see the blue color from all directions. But why does the sky look red or look orange during the sunset? So this is mainly because if we consider our atmosphere, okay, so let's say this is, I'm just using this laser pointer to draw a, let's say if I can draw that out. So for example, if this is our Earth, right? And then we know that when the sunset happens, that's basically a person is viewing the sun at this top direction, mainly because the solar radiation is not reaching to the back side of the Earth, right? So it's only shining on the front side. And when sunset or sunrise happens, this person is basically sitting on the top side, top location of this of our Earth right now. So we know that surrounding our Earth, there's a thick atmosphere, which is filled with gas molecules and also the particulate matter. So now if we just imagine again, so the air is filled with a lot of suspended particles, which means that the solar radiation, in order to reach to this top point, it has to penetrate a very thick layer of the atmosphere. So instead of penetrating a thickness like this, it's going to penetrate a thickness that's much larger or much longer compared to the location that's just directly facing the sun, right? And because of the thicker atmosphere and because of these larger quantity of particles, they're going to scatter the blue light on the way that the solar radiation is reaching to this person. So basically all the blue light is scattered out, and what finally reach to this person is going to be the red light. And that's why we can see a red or a yellow sky. Basically, it's giving us a warm color of the sky, right? So similarly, you may have seen this lunar eclipse, right? Before. So whenever this happens, people will say that, well, we're having a red moon, right? You probably also heard of blue moon, which is happened to be a beer, but there's also a reason why it's showing the blue color. But in terms of the red moon, this is associated with the lunar eclipse. And this is also because of the particles. And it's because of the particles or the particulate matter on the Earth. So now I'm drawing the relative location of the Earth, the sun, and the moon when the lunar eclipse happened, right? We know that basically the sun is shining on all directions, right? If it shines on the Earth, then it's basically give us a daylight. If it shines on the moon, then we can see the shined moon, right? Basically, that's gonna have we can see the shape of the moon. But when the lunar eclipse happens, basically the moon is in the shadow of the Earth, right? So that's basically what's happening under this situation. And then the red moon happens when the moon just reach to the side or just reach to the edge of this shadow, where the sunlight are going to penetrate through the atmosphere. So basically it's going to follow this line here. It's going to penetrate the Earth's atmosphere. And again, the Earth's atmosphere is filled with particles, right? And it's going to scatter all the blue light. And finally, what reach to the Earth's surface is going to be the red light. And that's why we're going to see this red moon when the lunar eclipse happens. As we said, these are basically the direct light scattering effect, right? So the particulate matter can also play a role in the Earth's climate. So when we say that the greenhouse gas species are leading to the global warming, actually the aerosols or the particulate matter can also play a role on our climate. And in general, there's a consensus that these aerosols can lead to the cooling of the Earth's climate. So it's kind of I would say a conflicting effect, right? Because for human emission, we're emitting a lot of greenhouse gas species that's leading to the Earth's warming. But at the same time, if we emit a lot of particles into the atmosphere, it's actually going to lead to a cooling effect. But this cooling effect is normally weaker compared to the warming effect. So that's why the global warming is going to be a trend, but it's not solely affected by the greenhouse gas species. To better show this, this cooling effect, we can just imagine, let's say there's a wildfire that's happening in in California, right, or the US West Coast. So directly out of the wildfire, we're going to see a large amount of smoke, right? So the smoke actually looks quite similar to clouds. So the cloud on the Earth actually play a major role in cooling our Earth's climate. This is mainly because the solar radiation, which is containing a lot of infrared or a lot of high energy, when they meet onto this white cloud here, they're going to get reflected back into the universe. So if you just imagine, let's say the Earth is covered by a cloud, well, it's going to look like a snowball, right? So if it's going to be covered by cloud, then the radiation that's emitted onto the Earth is going to be largely reflected back into the universe. And because of that, the Earth's temperature is going to get cooler. So basically, from these emissions, where we generate a lot of these larger particles, they behave quite similar compared to the cloud, which means that they can scatter light back into the universe and cause some cooling effect. But it really depends on what is the color of the cloud, because you see that this also has some grayish color, right? But if the smoke looks like black, then that's going to absorb all the energy and lead to a warming effect. So this is what people call the direct effect on the climate. Basically, these particles are going to scatter light back into the universe, right? And there's also an effect that's called the indirect effect. So the indirect effect is a result of these particles forming clouds. So as we introduced earlier on this slide, right? So the particles, they can basically get absorbed by the water vapor. They can grow into water droplets. And that's basically what's forming our cloud, right? So during this indirect effect, these particles can actually get grown up and form clouds. And we know that once these particles form clouds, they're just going to reflect light back into the universe, and that's causing a net cooling effect, right? So you may be wondering, well, is that indirect effect very important, right? Isn't this effect more important? But actually, it turns out that the indirect effect is very straightforward to understand, and it's playing a major role in controlling or in manipulating our Earth's climate. So in this satellite image, you can see that I think this is again an image of the US West Coast. So you can see that there are a lot of long stripes of clouds, right? Looks like this. So actually these clouds are not formed by nature, right? So basically what happens is that these are ship plumes. So there are a lot of traffic in terms of shipping in the Pacific Ocean, right? So when the ship pass by, it's going to emit some smoke into the atmosphere. So as they rise up, they're going to absorb more water, grow to larger sizes. And then at the top of the what we call the boundary layer, or basically the lowest layer of the Earth's atmosphere, they're going to form clouds. And that's why we're having these very long stripes of clouds, right? So this is a direct effect that's showing, or direct evidence that's showing how the aerosols may indirectly affect our Earth's climate by forming clouds, right? So I think 2 years ago, there's a major news that the Amazon forest is having fire, right? This is also during their dry season. I think there are also some political reasons behind that due to the demand from the farmers. So basically, this is another satellite image showing the wildfire season in the basically the wildfire event in the Amazon. So you can see that we can observe a lot of smoke, right? While these smoke are getting changed or getting faded into clouds, mainly because of this indirect effect. So basically, they're absorbing more water and then form these clouds over the region. So because of that, when we talk about humans' effect on the Earth's climate, we shouldn't just think about greenhouse gas species. We should also think about these particulate matter, which is largely calling a net cooling effect onto our Earth's climate. And this is actually a quite complex issue because for different altitude or for different regions of the world, if you just emit the same amount of the aerosols into the atmosphere, they're not necessarily going to form the same amount of clouds. For example, over the ocean, where normally we have just so little amount of aerosols, if you just emit a large amount of particles into the ocean surface, they may be forming clouds quite extensively, right? Because they're limited by these concentrations of the particulate matter. But if we're talking about the regions over cities, right, where the pollution is already quite severe, then this effect may not be very significant. So that's why there's a new subject or a new topic of research that's called the geotechnical engineering. Basically, people are trying to, or it's also called the climate engineering. So basically, people are trying to control or to modify our Earth's climate by some engineering methods. One of the methods is pumping in these large amount of particles into the atmosphere, right? And you may wonder how people do that. Actually, there are some designs coming out already. So people are imagining that, people are planning that we can probably send some ships and then just aerosolize the seawater, because we know that seawater, after they dry up, they're going to be sea salt. And they can serve as the particular matter that can further form clouds. So there haven't been any real applications of these ideas yet, because people want to understand what is the mechanism in terms of the indirect effect. So I would say that this is still a very new research, and we'll see in the following years what's going to happen on these directions. So in terms of the health effect of the particular matter, here what I'm showing is that basically for the same particles or a bunch of particles, they're going to have different deposition fraction in our human lung. So for example, here, I'm just dividing the human respiratory system into different regions, right? So we have the head airway, that's also called the extrathoracic region. Basically, this is just going to contain our nose or mouth, and then basically the throat, right? And then we also have the TB region, which is the tracheal bronchial region. So the TB region is mainly composed of these tubes, this major tube or the major branches. So finally, it's the alveoli region or the alveolar region, which is basically the tiny bubbles at the end of our lung. So for the particles that's getting inhaled by the human being, they're going to have different deposition fraction. Okay, so their deposition fraction is definitely not 100%, which means that you're not going to inhale all the particles. So it also depends on what the particle size is, right? You may think that the smaller the particle, basically the smaller the particle, the larger the deposition, but it's actually not the case. So generally, the deposition fraction will have a lowest efficiency or the lowest value at around 200 to 300 microns. So what that basically means is that once we inhale these particles, we're just going to exhale them out. They're not going to get deposited into our human respiratory system. So you can see a major trend that's basically decreasing with size and then increase with size and then further decrease. So the reason why we're seeing this decrease here is because the particles are just too large. So in our inhalation are not going to pick them up, right? The reason why we're seeing this this increase here, right, is because the particles are too small. They're going to diffuse and then further to get deposited. But the region in here is actually because of a combined effect. So you know that efficiency is going to increase. And you also know that the efficiency in here for the larger sizes, you're going to inhale them and then get deposited due to the gravity, right? For this region is due to the gravity or the higher inertia. So basically they're just getting collected. They cannot make these bends and then just collect it on here, right? So we know that the efficiency is going to increase with smaller sizes and also increase with larger sizes, which means that there's going to be a region where we're going to have the lowest deposition efficiency. We also call this range as the escape window, okay? So actually the reason why people defined particulate matter into different ranges is because of their size. For example, the PM10, when people talk about PM10, we're mainly mentioning or mainly referring them to these larger particles, okay? So PM10 can get deposited quite efficiently. Quite efficiently, I would say, in the head airway, right? The extrathoracic region. So the PM5 is mainly depositing in the TB region, while the PM 2.5 and PM1 is mainly depositing in the alveoli region, right? So they're depositing with different mechanisms. For example, for the very large particles, people call that impaction. It's because their inertia is too large. They cannot make these very sharp bends so that they got deposited onto the surface here. And for these very large particles, there's another mechanism called the interception, also because of the inertia. And for the very small particles, they have a large deposition because of diffusion. So basically, they can diffuse very fast, right? They can move very fast and then get deposited onto the surface. So because of that, let's say if you're a pharmaceutical company and you want to design a nasal spray for people with allergy, right? So we should control the size of these droplets, because nowadays, if let's say during the allergy season, we can just spray some medicine into our nose, right? So in that case, if we want to design the diameter of the medicine droplets, which range should we use? We should definitely not use this range, right? Because what this means is that if the droplets are in this range, once they get into our lung, we're just going to exhale them out. We should more likely design them into this range here, right? Because they're going to have a higher deposition, right? But if you're trying to make some medicine that can reach to the deeper lung, then we should make these particle sizes further smaller and try to deposit them into our lung. So as we have introduced earlier, we can also use this particulate matter to basically improve the performance of the functional nanomaterials. And you can see that we're in almost all aspects of our daily life, we're using these nanomaterials. So here I actually have a image that's showing the sunscreen components. You see that normally on the label, you can see that they are enriched in zinc oxide, right? So there are also some controversial applications. For example, the agriculture. People are trying to or proposing to use these nanoparticles that's containing phosphorus, which is quite useful, are going to be quite useful, because nowadays when people apply phosphorus, we're still directly using liquid or large chunks of these solids, and which means that we're not fully using all the component, because basically these nutrients are going to get infiltrated and then further leaked into the water body. We introduced that, and that's basically the nutrition in the water is going to cause some ecological damages. So people are proposing that we can maybe create some sprays similar to nasal sprays, right? These sprays will contain these nanomaterials, and then they can get absorbed more efficiently by the plants or by the crops. But they are indeed quite controversial, because if we talk about these nanoparticles in the food, they may contain some other types of components inside, or they may get absorbed more efficiently by the human body and cause some health issues. And we still don't know that, but this is definitely one way to go in the future of the agriculture. Right here, I'm also listing some numbers. Right, so the nanoengineering is becoming a quite significant area, and it's going to, I would say, the knowledge that we use on the particulate matter are going to be quite useful in these applications. So in terms of the some more detailed characterization of the PM, so people may have the question, well, how do we quantify PM, right? What properties are we interested in the PM? So we have introduced a little bit, right? So for example, the shape of the PM is quite important, right? If you just think about the suspended particles in the air, if they have the shape of spheres, and when we inhale them into our body, maybe we're okay. But if they have the shape of needle, then they may get basically puncture our respiratory system. And this is actually what's happening in mines, because in, in mines, there are some particles, for example, silicon oxide, which are also called quartz. They're going to have a shape of needle or shape of flakes, So they're going to have very sharp edges, and they can damage the miner's health or the respiratory system. So I would say the two major properties that people are interested in are the concentration of the PM and the size of the PM. So we discussed that how the recent study found that the concentrated particles generated by diesel engines or by engines might lead to brain cancer, right? So we specifically give some contrast. Let's say in major cities, the concentration of the particles are, let's say, 1,000,000 or 100,000 particles per centimeter cube. While in remote areas, the concentration is just a few hundred, a few thousand particles per centimeter cube. So definitely number concentration are going to play a role. But at the same time, the size of the particles are going to play a role as well. Because if you imagine, if most of the particles are in the range of this range, right, which means that people are not going to pick them up in our respiratory system. So that's going to be less severe compared to other sizes, right? So in terms of the size, there are definitions, for example, the physical size, the aerodynamic size, volumetric size, mobility size, and so on. But if the particles is spherical, let's say the most simple condition, and has a density of water, which we can make for most of the suspended particles in the air, all of these sizes are going to be the same. Okay, so all of these sizes are the same. The reason why I raised the point of the particle size is also because nowadays, especially under the COVID-19 pandemic, there are a lot of discussion on whether the transmission of the disease is airborne or not. So not right now, there are more and more evidence showing that this is an airborne disease, right? So they are going to affect the aerosol and droplet transmission of SARS-CoV-2. And actually, we can calculate how fast these respiratory drops can settle down to the ground, right? We know that the social distancing for two separate people are, or the recommended social distancing is 6 feet. But is 6 feet enough, right? Should we use longer social distancing or shorter social distancing? So actually, we can calculate how fast these particles can settle. So the way we do that is we can just build a mass balance or the force balance onto the particle. So let's say we have a spherical particle that's made of saliva if a person sneezes or cough, right? You have the gravity that's pulling the particle down. And then at the same time, you have the drag force that's existing onto the particle. So the drag force is what's stopping the movement of the particle. So you can just imagine that if a person goes skydiving, right? So it's not only the gravity that's pulling the person down, but at the same time, there's going to be a drag force that's pulling the person up, right? So because of the balance of these two velocities, that's going to give the settling velocity of the particle. So the drag force is calculated by 3 pi mu dp multiplied by v. So pi, we know that's just a constant. So mu is the viscosity of the air. So generally, the larger the viscosity, the more drag force, or the stronger the drag force. dp is the particle diameter, basically how large this particle is. And the Vs here is the settling velocity. Okay. So you see that further in here, the G is the gravity of the Earth, right? The M is just the particle mass, right? We can also calculate it with rho multiplied by V, right? So rho is the density of the particle. So V is the volume of the particle. So at the same time, basically, if you know what the size of the particle is, basically the diameter, you can also know what is the volume. That's just pi over 6 multiplied by dp to the cube, right? So basically, let's say if you know what the particle size is, and if we further assume that their density is water, we can actually calculate what is the settling velocity. And people have done that. So here, what I'm showing is that this is on the x-axis is the diameter of the basically the emitted droplet. And on the y-axis, it's the time for this droplet to settle down 1.5 meters. So you see that for particles of, let's say, below 100 micron, right? They're going to take at least a few seconds. If we're talking about particles below 1 micron, that's going to take, let's say, 2 multiplied by 10 to the fourth. That's going to take a few hours for the particles to settle down. So you may be interested in what is the typical size of the respiratory droplet, right? So people have measured that before. The mean size of a respiratory droplet is around 10 micron, okay? So you can see that for a 10 micron particle, it's normally going to take around 8 minutes for them to settle down. And people actually have calculated what is the air velocity that's coming out of the sneezing. So if we just use this velocity to plug it in, because we already know what is the size of the particle and we know what is how long it needs to settle down, we can calculate how far it can travel, right? You see that it can travel for more than 10 meters, which means that the 6 feet may not be sufficient for us to protect each other, right? So what the really the 6 feet, I would say, it can do is we're basically stopping a lot of these larger droplets, right? So the larger droplets, they're going to have a larger gravity, right? It can settle down for longer, for basically for shorter time. And that's going to reduce the transmission risk. But of course, I would say the 6 feet is also quite a compromise because theoretically, we cannot just let people to separate by 10 meters. Otherwise, how are we going to take the classes? How are we going to do some, let's say, in the hospitals or in the playground, right? There's no way that we can maintain each other safe. So that's why under this situation, wearing a mask is going to be very important. So nowadays, there are also a lot of studies regarding the design of the masks. But before that, I just want to show some recent results, I would say recent findings regarding the airborne transmission of the SARS-CoV-2. So basically, what's shown in here is the measurement of the airborne particles or the bioaerosols that's emitted by people with symptoms of flus. Okay, so this is influenza A. So people have actually collected these particle samples in different locations, for example, health centers, or the daycares, or the airplane. And then people also categorize them into different sizes. For example, this is just talking about PM 2.5, right? And we further divide them into different size ranges. So you can see that in terms of the flu, let's say quite a large fraction of them are, let's say, above 2.5 microns. Okay, so it really depends on which location we're talking about. For example, in the daycare, it's mainly particles larger than 2.5 microns. But if we're talking about health centers, it's mainly particles in the size range of 1 to 2.5 microns. So people should do these size-dependent measurement to determine basically how long these particles can settle down, how long they can get floated in our indoor air to know what is the risk, right? So what this is showing is basically a study of last year, which is measuring the SARS-CoV-2 RNA in different size bins. So this is similarly talking about these 5 different size bins, right? And then you can see that this is measuring the SARS-CoV-2 RNA concentration in different regions of a hospital. For example, there's a Fangcang hospital, and then basically this is the protective apparel removal room, or in different zones, right? You have zone B, zone C, and then the medical staff office. So you can see that we can indeed measure these SARS-CoV-2 viral RNAs, and they're existing in a very small size range, 0.25 to 0.5 micron. So if that's the case, if you just look at the calculation, we're talking about 0.25 or 2.5 micron. And then we're talking about a range in here, 0.25 to 0.5, right? We're talking about a time range in here, which means that they're going to just settle, they're going to suspend for more than 10 hours or more than 12 hours. This is going to pose a quite significant risk to the health of both the medical workers and also the patients if they don't have these viruses, right? So I would say that the airborne transmission of the SARS-CoV-2 is a quite concrete phenomena, right? So we should follow the science for sure. And then as I introduced, we should wear masks, okay? So during the pandemic, there are a lot of inventions or the DIY masks or basically masks with different materials. So there are better ones, for example, the N95. Of course, we shouldn't use this because this has a valve. So what the valve does is when a person exhale, the air is not filtered, which basically means that it's not going to protect the people surrounding this person. So if you happen to wear a N95 mask, try to make sure that it doesn't have this valve here. So we also have the typical surgical masks or the masks that's made of these cloth, right? So all of them can work in terms of stopping the particles. But again, this stopping efficiency or this filtration efficiency is going to depend on the particle size. And this is what we have been working on in our group to characterize the filtration efficiency of these different materials, or fabric materials, or these N95 materials as a function of particle size. So you can see that this black line here actually shows you the filtration efficiency of N95 materials in our laboratory setting. So basically they have a very high efficiency, right? So the reason why they're called N95 is because these materials need to achieve a efficiency that's above 95% at a particle size of around 300 nanometer or 0.3 micrometer. So you see that this one is close to 95% efficiency, right? So there are a lot of fabric materials as well, because I remember at the beginning of the pandemic, the CDC recommended people to use the bandana or use the scarves to protect themselves, to basically remove these particles or filter these particles. But as it turns out, they actually have a quite low efficiency in blocking these particles. So of course, there are some other fabric materials as well. For example, we tried pillowcases that has different thread counts. Basically, the 600 thread count pillowcases are going to be more densely weaved, right? So they're going to have a better blocking efficiency, but at the same time, they're going to increase um, the flow resistance. So basically, it's going to be more difficult to blow through this fabric material. But what we found is that actually the furnace filters can achieve pretty high efficiency in blocking these particles. So you see that if we just stack 4 layers of these furnace filters, they're going to achieve at least 80% efficiency, but at the same time, the flow resistance is quite low compared to the N95 materials. So if you're interested, we have a table that's shared on Google Drive, and I can give you access, or I can give you the link later on, so you can check what are the filtration efficiency for common fabric materials. And of course, if you're interested in this study, we have all the setup ready. We can just test more materials and to find out what is their performance in blocking the particles. So as I said, the particle size is a very important parameter, right? So basically here in this table is showing all different types of particles and together with their sizes. So for example, if we're talking about the fly ash that's emitted by coal-fired power plant, they generally have the size of around 1 to 100 microns. If you're talking about black carbon, which is the additive in the tires, right? Their size is going to be smaller, mainly because these black carbon have to be conducted from the combustion at a very high temperature. So then you may wonder, how do people measure the size, right? Are we going to just collect them and look them under the microscope? Actually, there's a quite easy way to do these measurements. So one of the most widely used setup to measure the size distribution is called the impactor. So by the way, the size distribution basically will give you the particle concentration as a function of size. So let's say, for example, if you have the particle size plotted on the x-axis, and then the concentration on the y-axis, and then if it has a shape like this, right, it means that it's going to have the highest concentration at this size here, while the concentration at lower sizes are going, other sizes are going to be lower. So what we call this curve is a size distribution. So people invented these impactors to measure the size distribution of the particles. The function of these setups are basically, first you have a relatively large particle that's being introduced, or you have a mixture of particles, let's say, particles with medium sizes, very large sizes, or smaller sizes. So when they're introduced into a setup that has a basically a collection plate right below the inlet, most of the large particles are just going to get collected, mainly because their inertia is too large. They cannot make this bend across the channel, right? So we're going to collect these very large particles here. So then after the first stage, the remaining particles are introduced into the second stage. So if you see, the major difference between these two stages are, first, the inlet diameter becomes smaller, which means that the airflow is going to get accelerated. They're going to have a larger velocity. But at the same time, the distance between the inlet and the collection stage are shorter, which means that we're going to start to collect particles of medium sizes, because these medium-sized particles cannot make these bend, mainly because their velocity is larger, right? Their inertia is increased again. So we're collecting the medium-sized particles in the second stage. Further, you see that the third stage, the inlet is further narrower, and then the distance is further shorter. So we're going to collect particles of small sizes or fine sizes. At the end, we're going to collect particles of very, very small sizes. Well, there will be particles of further smaller sizes which we cannot collect them with these impactors anymore. So that's why people also use the filter at the end to basically trap all the particles. And once we collect these particles, we can just measure the weight to calculate what is the mass of the particles on these different stages, and then convert it into the number. So this is a simple way to measure the size distribution of the particles. And then here I'm going to show a few videos about how do we control the particulate matter. So basically in industry, for example, the combustion, the coal-fired power plant, we're emitting a lot of fly ash, a lot of very fine particles into the atmosphere. And if we don't control their emission, it's just going to pollute the atmosphere. So that's why we have all different types of setups to basically control the emission of these particles. There are setups with very low, pretty low efficiency, with medium efficiency, and very high efficiency. So here, what I'm going to show is a setup that's having a, I would say, a medium efficiency.
Hurricanes are customized cyclones to serve different needs, and which results from optimization functions such as maximize efficiency, minimize cost, or minimize size, combining stochastic numerical optimization by changing the 8 independent cyclone dimensions with knowledge of particle agglomeration. ACS is able to design the perfect geometry for each case. The colored dots indicate the particulates to be collected, and the blue arrow represents the flow of gas that leaves the equipment. For dusts with tendency to agglomerate, such as biomass or coal fly ash, among others, efficiency is maximized thanks to the clustering effects of particles. In fact, the cyclone doesn't see as many small particles, but clustered particles with bigger dimensions, and thus easier to collect. Agglomeration increases with wide particle size distributions, long residence times in the cyclone, and large inlet particle concentrations. Agglomeration is maximized with the new developed Hurricane MK cyclones. Emissions can be under 15% of those of other cyclones, being as low as 30 milligrams per normal cubic meter for many industrial processes.
Okay, so this setup is called the hurricane, or people also, most of the time, people just call it cyclones. So basically, it's using the mechanism of a cyclone. We're going to create this strong rotational, or this revolving movement of the air. And because of the higher inertia of these particulate matter, they're just going to hit onto the wall and then further get collected. So the cyclones are quite widely used in all the PM control devices or the PM control facilities. So if you're interested, I think right now, of course, we know that the coal-fired power plant of our campus is being disassembled, but I think the cyclone is still nearby. Okay, they still haven't taken the cyclone away. So next time when you walk by, you can take a look, right? And then you can have a better understanding of how it works. So you generally have these cylindrical shape, right? The air is going to rotate or revolve within these channels here. And then basically the particles or larger particles are getting collected at the bottom while you are going to get this cleaner air getting emitted. So for the cyclones, the collection efficiency, I would say, is normally below 60%, below 70%, right? So it's not a complete removal of the PM. So that's why the cyclones are also used or generally used as a pre-cleaner to basically pre-treat the flue gas coming out of the coal-fired power plant or other industrial processes. So the second setup I want to introduce is the electrostatic precipitator, or the ESP. So what happens is that here we're going to use the electrostatic force to remove the particles. Again, I have a short video which I'm going to show briefly how it works.
A precipitator operates in an enclosed chamber. Inside the chamber are collection plates that are connected to the grounded outer frame. Positioned around the collection plates are discharge electrodes. The electrodes are negatively charged with high voltages and are insulated from ground. As flue gas flows through the chamber, dust particles and other entrained flue gas components pass through the high energy field and become ionized. This drives negatively charged ions and particles to the collection plates. The particulate matter builds up on the collection plates and forms a layer.
In the ESP, what we do is we first use these thin wires to generate a lot of ions, right? The ions are going to attach onto the particles, and then we have these collection plates to collect these particles, and further, we can vibrate them and then let these particles to settle down. So the ESP is a quite efficient method. It can remove almost 97 to 99% of the particles. But still, some particles, for example, very small particles, they're not going to get charged by the ions, right? They can still get emitted or escaped from the ESP setup. And in order to achieve a full removal or full capture of these particles, people designed the filters. So what happens is that we can introduce these dirty gases through these filter bags, what we call filter bags. So these filter bags are just going to be a layer of bag. Just think of the plastic bags, except that you have tiny holes on the plastic bag, right? So the air is going to penetrate through the holes, right? But most of the particles are just captured by these bag here. So I shouldn't say most of the particles, but all of the particles are captured by the bag. And then we can shake these bags and then let these particles to settle down and further get collected at the bottom. So again, I have a short video which can briefly show you how the filter bag system works.
There are many different sizes and designs, but baghouses all operate in the same basic way. 1. The dust-laden or particle-laden air or gas stream enters the baghouse, travels along the surfaces of multiple fabric tubes, and then passes outward or inward through the fabric. 2. The larger particles fall down into a hopper, while the smaller particles accumulate on the fabric surfaces. 3. A cleaning mechanism occasionally removes the particles from the fabric tubes, and they fall down into the hopper from which they are discharged. 4. The clean air or gas stream exits from the top of the baghouse.
Okay, so you can see that basically these filter will achieve a complete capture of these particles, right? So I would say that normally in coal-fired power plants, what people do is that they're going to use a combination of the cyclones and the ESP. So what happens is that the cyclone is going to pre-treat the particles, right, to remove, let's say, more than half of the particles, the larger particles, and then the ESP will remove the rest of the particles. So combining these two together, we can achieve a pretty high efficiency. But in terms of the filter, which does a complete removal, its maintaining cost is going to be higher, because it comes with a price, right? And also the pressure drop, I would say the flow resistance through the filters are going to be higher compared to these two setups. So that's why when you operate them, they're going to cost more, but you're going to achieve a full capture of these particles. So the filter systems are used when we know that the particulate matter are very toxic. For example, some chemical processes that's dealing with the heavy metals, right? We don't want to emit these heavy metal particles into the atmosphere. So that's why we want to use these complete capture setups to remove these particles from the flue gas. Okay, so this is about the general contents of the particulate matter and the PM control. So we can also use the rest of time to briefly talk about the gas pollutants. So in this course, we're just going to talk about the sulfur dioxide and nitrogen dioxide, although that we know that there are other gas species, for example, the ozone, the carbon monoxide, but the sulfur dioxide and nitrogen dioxide are, I would say, the more important ones, and they're using a similar mechanism to be captured. Okay, so as we introduce the sulfur dioxide, nitrogen dioxide, they are criteria air pollutants. They can get deposited into our human respiratory system, lead to asthma or inflammation, right? And once they're emitted into the atmosphere, they're going to cause acid rain, which is acidic and is going to harm the plants or the properties. So before we introduce how to capture them, we need to first know how to understand their quantity. So here in this table, I'm again showing the EPA standard that's showing the basically what are the limit of these pollutants, right? To tell whether the air is good or bad. For example, if you check the nitrogen dioxide, there are two concentrations for the annual arithmetic mean. So what happens is that you can see these two values. One is 0.053 ppm, the other is 100 microgram per meter cube. Okay, so are they the same or are they different standards, right? So how do we understand these concentrations with different units here? So before we introduce how we control them, we need to first know how do we convert from different units to another unit, right? So if you look at these two units, they're basically representing different concentrations. So the ppm, we will call them mole fractions or the number fractions, right? For example, 1% is a number fraction. So basically this ppm is just showing how many moles are these gas pollutants in all the number of moles of the gas species. While the microgram per meter cube is a mass concentration. It represents what is the mass of the nitrogen dioxide in a cubic meter of the gas mixture, okay? So how do we convert from each other, right? And then here, I'm showing 3 example problems. I'm just going to guide you through the first one, which is converting 1100, let's see, 1100 milligram per meter cube carbon dioxide into ppm, okay? So if we just look at the problem here, we're provided with the mass concentration, and we can write them out as MA divided by V, right? So A here represents the species of A. It's basically the mass of the carbon dioxide divided by the volume of the entire gas mixture. So the ppm, as we said, is a mole fraction. So if we just want to write that with symbols, that's going to be NA divided by N, where N is the total number of moles in this gas mixture. Okay, so in order to convert one from the other, we just need to use the ideal gas law. So we know that the ideal gas law is PV equal to nRT. I know that some of you also call it Tavernert, right? So the ideal gas law, this is for the entire mixture. And actually, the ideal gas law also works for a single species. For example, it works for the carbon dioxide although it's just very well mixed in the gas species, right? The way we write it out is PAV equal to NART. So here we call PA as the partial pressure. So basically, if we have a fraction of carbon dioxide in the gas mixture, its partial pressure is going to be smaller, right? Because it's not filling the entire volume here. And at the same time, we have the relationship of Na divided by N equal to PA divided by P, which is just showing you that the mole fraction is equal to the partial pressure divided by the total pressure. So further, we know that in terms of the number of moles and the mass, we know that number of moles is equal to mass divided by the molecular weight of the A species. So we can just use these four equations to derive the relationship. Okay, so you see that for the Na divided by N, we still have PA divided by P, but at the same time, you see we can calculate PA from this equation, which is just NART divided by V, and then we further divide that by P. And then how do we calculate Na? So we have Na in here, right? That's just the mass of A divided by the molecular weight of A. So basically, you can rearrange it. You can pull the V out, right? You're going to have Ma divided by V multiplied by RT divided by molecular weight of A multiplied by P, okay? So basically, this is how we convert from one to the other, because here we're having the mole fraction, and here we're having the mass fraction, or the mass concentration. And all of the rest are just going to be constant, right? R is the ideal gas law constant, right? Or the gas constant. T is temperature. We should know that the temperature should be in Kelvin. Molecular weight of A, we should know what it is for carbon dioxide. And then pressure is the total pressure, right? That's just 1 atmosphere. So similarly, we can do the conversion from basically the mole fraction to mass fraction. We just rearrange this term, right? So basically, we're trying to derive what is the mass concentration in terms of the mole fraction here. So with these two equations, then we can convert these units, right? For example, for the carbon dioxide, or the first problem, basically what we have is the mass concentration of A, right? We want to know what is the mole fraction, ppm. So we should directly use this equation. So Na divided by N is going to be 1100 multiplied by 10 to the negative 6 kilogram per meter cube. So note here that we have to use the standard units, or the international units, right? So milligram is not a standard unit. We need to convert it into kilogram. So that's why we need to multiply 10 to the negative 6 to get kilogram per meter cube, right? So this is the basically the mass concentration in this term here. So the R is the gas constant, 8.314 multiplied by the unit is joule per mole per K. The T is the temperature in Kelvin. That's 233.15 plus 25 Celsius. This is Kelvin. And then we divide the things in the denominator, right? We have the molecular weight of A, that is carbon dioxide. You have 44 multiplied by 10 to the negative 3, because we know that the molecular weight of carbon dioxide is 44 grams per mole. But in terms of standard units, we need to further multiply by 10 to the negative 3 kilogram per mole, right? And then the pressure is 1 atmosphere. We need to convert it into Pascal, right? So this is going to be the entire unit, or the entire calculation. And you can just pull out your calculator and see what answer you get. So basically, you're going to get 0.000611. And it's asking for ppm. So ppm means parts per million, right? Basically, it means how many parts are there in a million molecules. So we can just multiply this number by 10 to the 6 to get 611 ppm. So this is how we convert the carbon dioxide in mass concentration into mole fraction. And I would say that with this equation here, it's going to be quite straightforward. All right. So for the remaining 2 questions, that's going to be your homework regarding the ideal gas law, or this unit conversion. So we said that these sulfur dioxide or nitrogen dioxide are going to lead to acid rain. And here I'm giving a picture, or 2 pictures of the famous Indian construction, right? This is Taj Mahal. You can see that this is actually not because of the sunlight, not because of the light scattering that we introduced earlier. It's just that the Indian government actually spent a lot to basically to furnish the surface of the Taj Mahal. And this is mainly because the acid rain is going to give it a yellowish color. So they have to basically remove the surface layer and then change it, or basically bring them into the original white color here. So the acid rain is also causing ecological damage. So if you go to the Smoky Mountain, there's a famous location called the Klimas Dome, where you can basically overlook the entire area. So on top of the Smoky Mountain, there are a lot of trees are actually caused or damaged by the acid rain. And this is basically it's going to remove their leaves and then cause a lot of ecological loss in terms of our forests. But actually, people are doing pretty good in terms of controlling the emission of the sulfur dioxide. So this is again showing the how the sulfur dioxide emission is decreasing after we establish the EPA, right? The concentration almost, or the emission almost decreased exponentially, and we were doing a very good job. And the device that we use to remove, or device that we can do this good job, is called the flue gas desulfurization, or the FGD. So the sulfur dioxide is mainly emitted by the coal-fired power plant because we need to use energy. So people design a system called lime scrubbing to remove the sulfur dioxide. So this is almost similar to a acid-base reaction. If you just consider, if we just add sulfur dioxide and then let it add it into water and then just throw calcium carbonate into the water, what's going to happen? Because the sulfur dioxide is a stronger acid, right? It can first get converted into sulfuric acid, and then get oxidized into basically get oxidized into sulfuric acid. So basically they can get further, and also the sulfuric acid is going to react with the calcium carbonate to form the calcium sulfate, right? So the calcium sulfate is a species that has a pretty low solubility. And that's why they can get settled down to the bottom of the scrubber. And then the way we distribute this system is that in the flue gas, we're going to contain a lot of these sulfur dioxide species, right? And then in order to let them react, what happens is that we first generate these limestone and then mix them with water to form a slurry, right? And then we pump it all the way up to a spray tower so that we can generate these tiny droplets, and they can get in contact with the sulfur dioxide gas species and then further react, right? So in order to conduct the oxidation, basically to convert sulfur dioxide into sulfur trioxide, right? To get sulfuric acid, we can further add in oxygen at the bottom of this limestone scrubber, and then to form the calcium sulfate, right? So again, I have a very short video to talk about this, this setup here.
In some instances, sulfur dioxide from combustion is removed from the flue gases by using it either to produce sulfuric acid or gypsum for construction. These products can then be sold to help offset the cost of running the flue gas desulfurization plant. In both cases, oxygen is used to help encourage the necessary reactions that need to take place. In the case of sulfuric acid, adding excess air to the sulfur dioxide and vanadium oxide converts it to sulfur trioxide, SO3. When combined with water, this produces H2SO4, or sulfuric acid. In the case of gypsum, limestone slurry used in wet scrubbing processes combines with sulfur dioxide to produce calcium sulfite. When subjected to a forced oxidation process involving the addition of water and oxygen, the sulfite is converted into gypsum. In addition to these processes, Oxygen is also required in flue gas desulfurization processes using seawater. As the seawater absorbs the sulfur dioxide, oxygen is added, creating a mix of sulfate ions and hydrogen, which in turn converts to water and CO2 gas. In all three cases, using an oxygen probe to accurately measure oxygen concentrations can help to regulate the conversion of sulfur dioxide.
This is about the control of the sulfur dioxide. And in terms of the nitrogen dioxide, as we introduced, nitrogen dioxide species, they have so many different types of components. For example, nitrogen dioxide, nitrogen monoxide, and then N2O5, right? These are the common forms of the nitrogen oxides. So that's why people also call them, or prefer to call them, nitrogen oxides groups, or just simply NOx, right? So its similarity with the sulfur dioxide is that it can cause human health problems and lead to acid rains. But the distinctions from the sulfur dioxide is that it's composed of groups of oxides. And in terms of the sources, half of them are actually coming from vehicles, and the other, I would say one third of the species are coming from the stationary sources. For example, just combustion processes. And in terms of the control of the nitrogen oxides, people have done a lot regarding how we can control it during the combustion. So here what I'm showing is that the concentration of the nitrogen monoxide, which is a major species of the NOx under high temperatures. And this is during just normal coal combustion. And you can see that as we introduce the concentration of the combustion, let's say we just follow this line here. As we increase the temperature of the combustion, the concentration of NOx increased almost, significantly, right? And you can see that because of that, in order to control the emission of the NOx, we need to reduce the combustion temperature, right? And at the same time, this is showing three different curves. One is with the shortest time, residence time, one is with 0.1 second, and one is with 1 second residence time. And if we just draw a vertical line here, what you can see is that if we have a very long residence time of the flue gas, we're also going to have a very high concentration of the NOx, right? So just based on the experimental data, what we can observe is that the higher the temperature, the more NOx, and also the longer the residence time, the more NOx, okay? So in order to deal with the NOx system, the NOx problem, what we can do is that we can reduce temperature, because temperature definitely play a role, right? We can also reduce the gas residence time so that the time in the hottest part of the flame zone is reduced. And in order to reduce the combustion temperature, what we can also do is to reduce the oxygen content in the flame zone, right? So that's why people came up with the method that's called the overfire combustion. So what the overfire combustion means is that instead of just mixing the fuel and the gas all in the same mixture, we're just going to conduct the combustion in multiple stages. For example, in this setup here, these white plumes are just normal air, okay? It doesn't have any fuel inside. But in the flame here, we're not providing enough of oxygen. So basically it's burning in a fuel-rich condition, which has a lot of fuel inside. So because of that, the combustion temperature is going to be lower, right? And then that's going to reduce NOx formation. But at the same time, those escaped fuel, they're going to rise up because their temperature is higher. They're going to mix with the air and then do the rest of the combustion. So we're still completely burning all the fuels, but we're significantly reducing the temperature of the combustion. And this has proven to be a very effective way to remove the, I would say, to remove the NOx formation from the combustion. So people have also done or created some other methods to remove the NOx from the gas streams. So for example, the selective selective catalytic reduction. So instead of doing that in combustion, we can just add some catalyst to let these NOx species to get reduced back into nitrogen. So people can also use the selective non-catalytic reduction, and then some other methods as well. But I would say that the SCR method is still the most widely used method. So here I also have a video link, but this is a overview of the entire coal-fired power plant. I would say if you're interested in the contents, you can feel free to go over the video. Okay, so that's all for this class. So this class, we covered quite a lot of contents. We talk about the particulate matter, their control, and also the unit conversion for the gas species, and also their control methods, mainly for the sulfur dioxide and nitrogen dioxide. So just feel free to let me know if you have any question. On Wednesday, we're going to return to the regular form of the class. We're going to talk about the atmospheric dispersion of these gas species, which is also quite important. All right, see you on Wednesday.